Yes, thank you very much for the introduction. Yeah, today I will present a work that I'm very excited about. Been working on together with my advisors, Bernhard and Michael. And I hope my excitement is contagious and you will also be excited about PENEX, which is a loss function that we introduce. And to get things started, I'm interested when you are presented with the task of training a classifier, what loss function do you typically use? Maybe suggestions from the audience. You can just speak up. You don't need to raise your arm. Cross-entropy, right. So most people, they use cross-entropy, and today we want to question that. We will look at a different loss that has different characteristics. And maybe I can also convince you to try out PENEX, which is this alternative that I'll present to you today. But we'll have to take a somewhat bizarre detour because we'll start with AdaBoost, which seems to have nothing to do with loss functions. But I'll guarantee you that at the end, things will fall into place and you will understand why we took the detour. Because AdaBoost is actually an ensemble learning technique, and ensemble learning is all based around the concept of a weak learner. A weak learner is a machine learning model that performs just a tiny bit better than flipping a coin. For instance, such a decision stump, what it does if it's presented with the task to classify whether someone has a disease, it's going to say, well, if you're older than 60 years old, you have the disease, otherwise you don't. It's not a good performance, but it's just a tiny bit better than guessing, and that's all that matters. Of course, we want a strong learner, and so what AdaBoost does is that it creates such a strong learner by taking a linear combination over many such weak learners. The question is, how do we fit this? How do we get to the strong learner? And the way that AdaBoost does it is by a greedy optimization. So again, F here is the strong learner. It's a linear combination over the weak learner's GI, and they sequentially minimize this exponential loss function. So this is very important. It's an exponential loss function, and we're in a binary classification setting. So we have labels -1 or 1, and we can get a feeling for how it behaves. For instance, if F is large and the true label is -1, then we get a very large penalty on that mistake, and vice versa. Now, AdaBoost works very well, and people were actually very much fascinated because they thought that it would overfit at some point. So you keep adding weak learners, and generalization keeps improving, but there never comes this point where the generalization worsens again. And people were very much confused and fascinated by this at the same time. And Leo Breiman, he went as far as to say that AdaBoost with decision trees is the best off-the-shelf classifier in the world. So there seems to be some magic happening in AdaBoost. And my goal for this project was to translate that magic to training deep neural networks. And our hypothesis here is that the secret sauce of AdaBoost is not even related to ensemble learning. It has nothing to do with ensemble learning. The magic is the exponential loss. And so this is what we'll take a closer look at. Of course, we're not only interested in binary classification, but we want to do multi-class classification, right? And there has been one prior work on extending the exponential loss and AdaBoost to the multi-class setting. Again, here on the left, we recognize the exponential loss. And then we have this constraint here on the right. Now, we note here that we don't only have one F as before, but we have one F for each class. And I'll call these logits from now on. This is really in neural networks the thing you put into the softmax. And now you may wonder, well, why do we need this weird constraint that the logits, they always sum up to 0, right? So we have K classes and they always need to sum up to 0. Why not just only use the exponential loss? And the simple answer to that is, well, if we would do that, then all the logits would just go to infinity. They would all diverge because we can make the exponential loss arbitrarily small by just making all Fs very large. So this constraint is really just to keep the logits from diverging to infinity. However, anyone who's ever tried doing constraint optimization with deep learning knows that it's a pain. What we really want is we want to have an objective that we can just apply Adam on, right? And that is the contribution of this work. Here we have a new formulation that is called penalized exponential loss, or PENEX for short. Again, we have the exponential loss slightly generalized. Now we have a parameter alpha that we call sensitivity parameter. And we now add this obscure thing on top of it. And we see that it fulfills a similar purpose to this zero-sum constraint. So it tries to keep the logits from diverging, but it does it without a constraint. So we can just train a neural network with Adam on that. Our first question is, does it work? Answer is yes. So here we have Cypher 100. With cross-entropy training, we see that in the early training epochs, generalization keeps improving, but then becomes worse. This is like this quote-unquote overfitting. And we can get rid of that by, for instance, label smoothing. It generalizes a bit better, so it goes a bit higher. Higher here means better generalization, but then it levels out, and PENEX, very much like AdaBoost, seems to just keep improving for much longer than label smoothing. And of course, we don't only have this for Cypher 100, but also for other data sets and metrics. But I personally think when we develop new method, it's important that we don't only have them work well, but also that they're theoretically grounded. So we want to look into the theory. And one property that PENEX fulfills is called Fisher consistency. It's introduced by Ronald Fisher, and it's defined in a single sentence. When applied to the whole population, the derived statistic should be equal to the parameter. What does that mean for PENEX? Well, in PENEX, we minimize this thing. So it's an empirical expectation, and the population level equivalent of that is just to replace the empirical expectation by the true expectation. And now we consider the minimizer of this. So the minimizer logits, we call them F star. And now Fisher says that we should be able to recover the true parameter from F star. Well, what is the true parameter? It's the best thing we can hope for. It's the Bayes optimal classifier, right? It turns out that the Bayes optimal classifier, the probability of y given x, is related to this optimal logits, like in the following way. So it's really just a softmax with a slight rescaling of the temperature. I guess when you guys think of regularization, you probably think of this. You have a cross-entropy loss, or more generally, a negative log likelihood, plus, and then something on top of that. So this encompasses label smoothing, L2 regularization, confidence penalty, and many others. And some textbooks, you will even find regularization be defined like this. And what all of these formulations have in common is that they're not Fisher consistent. What is the reason for that? Cross-entropy loss itself is Fisher consistent. And then this penalty that we add on top of that is pushing us away from that. If the last few slides were a bit too fast for you or something, I have also a visual analogy to bring the point across. Let's say we want to have a pretty car, and pretty car here corresponds to Fisher consistency, and we also want it to generalize well. And generalizing well in this analogy corresponds to having at least 4 seats. Oh, can we see this here? Oops. What do I have to press? Ah. Yes, so in this analogy, you can think of PENEX as a pretty car that has 4 seats, even has 5 seats, because it generalizes very well. And these usual formulations of cross-entropy loss plus something is more like a car that used to be pretty, but it only has 2 seats, right? So we somehow mount these 2 extra seats on top of it. So we can carry around 4 people, but now it's not a pretty car anymore. At least it's not a car that I would like to drive. Okay. But we still didn't really get into why it works. Oops. We still didn't really get into why it works. Yes, Max Planck says insight must precede application. I agree. And our argument is a type of implicit margin maximization. So you know this principle from SVMs potentially. The margin you can think of as the distance from the data points to the decision boundary. And what PENEX does very similarly to SVMs is that it tries to keep the decision boundary away from the data points. And this does not happen with cross-entropy. We see this on the right. So here we have a data point that's very close to the decision boundary. We can also prove this formally. Here we define margin a bit different. It's not exactly the same as the distance to the decision boundary, but it's a related definition. So here we define it as the difference between the true logit and the maximum wrong logit. And we can prove that the probability of the margin being small is small if PENEX is small in expectation. All right, so let's summarize what we've learned today. First of all, the AdaBoost magic can be translated to neural networks. My hypothesis is the magic has nothing to do with ensemble learning. The magic comes from the exponential loss. PENEX is the means to translate this magic to neural networks. We have no constraints. We can just optimize this. Then second point, regularization is not at odds with Fisher consistency. You can have a nice looking car that has 5 seats. Then we looked into why does PENEX generalize well? Well, it implicitly maximizes margins. It's well known in earlier work. One can show that maximizing margins is related to good generalization. And finally, this is a bit more of a subjective point. I think we should question the foundations more because there's a lot of interesting things to discover. When you see a loss function that everyone uses, don't just use it to question, is this really the best thing or is there something else we could use instead? Yes, and with that, I'm happy to conclude. If you're interested, there's a preprint and code. Also, if you want to try out this loss in your new project, it's minimal effort to integrate it. So really, you just replace cross-entropy loss by this. It's very simple.